Welcome to the Checking All the Right Boxes webinar here at EDX. Thank you for taking some time to learn more about the tools and best practices with us. My name is Rory Fox, and in just a few moments, Brian Jones will take the floor to cover helping you understand how to determine the best path loss model selections for your particular use case. He will cover various study types and propagation models for mobile versus fixed applications in SignalPro. If you have any questions during the webinar, you can use your webinar pane on your screen to submit them, and we'll answer them towards the end of the webinar. Sit back and relax because away we go. Brian, the floor is yours.
Thanks, Rory, and thank you everybody for signing up and attending this morning. I wanted to take some time today and really dig into the dialogue that we're looking at here, the propagation model dialogue, and talk in detail about some of the options that are available with SignalPro on its own and with SignalPro with some additional modules, and to really talk about how to make sure that the modeling you're doing in SignalPro matches the real world use case that you're trying to design for as closely as possible, and also make sure that you understand the places where that model may be imperfect or may not be totally representative of what you're going to find out in the field, so that hopefully you can account and make allowances even for the discrepancies that are invariably going to be there between your predictive model and your real world results when you deploy a network. And there are a number of issues that have come up in trainings across the various industries and niches of RF design that I find the same issues coming up again and again, and some of the same questions. So for many of you, this will probably be somewhat remedial, a lot of it, but hopefully there will be something new or something you hadn't quite thought about in your own projects. And of course, if this is all new material, like Rory said, please feel free to enter some questions as we go along in the chat window, and we'll try to address some of those at the end. So what I'm concerned with today is establishing mostly just the propagation model options and the study type that we're going to be doing in SignalPro, and that is to say the path loss model. The fundamental thing that SignalPro does and builds nearly all of its predictive results on is a prediction of the path loss between any two antennas, be that a base station and a mobile remote unit, or a point-to-point backhaul link. There's always going to be that air interface section between the two antennas, and we're trying to account for the path loss in the environment. And then all of our other predictions for signal-to-noise ratios and predictions of the data rate and the performance of your different systems, those are really all based on that path loss model. So if that model is not terribly representative of the environment, then all of the other results can be off as well. And so this dialogue is really kind of the linchpin of getting good, reliable results from SignalPro, regardless of what the technology is that you're studying and what the actual topology of the network is going to be. And so we're going to drill into this dialogue and really look at all the options. So when I first get a hold of a project and start to think about how to model this in SignalPro, it's important to think about sort of these questions. Initially, am I doing a dimensioning estimate? So is this a rough number of sites that should be needed to cover a service area for sort of an RFP proposal type of a thing? Am I just trying to get a rough number, or am I really trying to do a finished design where all of my antenna selections need to be correct, and I need to model exact heights on the towers and all of that stuff? if I'm just doing a rough dimensioning estimate, maybe I don't need to have super high resolution terrain and clutter and all of those things for my model, but I can get away with something sort of faster and looser. And we'll talk about that a little more in detail. But then the next one is, what is the topology of the network? And by that, I mean, are we talking about tall base stations that are elevated up above the surrounding clutter, and then mobile remote subscriber units that are down moving around through the environment and oftentimes very close to the clutter? Or are we talking about fixed assets, point-to-point backhaul links, or in some of the utility cases, very often we have assets up on the top of utility poles or light poles or something like that, and they're going to interact differently with the clutter along the paths. You know, each of those fixed links is a very precise path that's going to be more predictable than a mobile remote type of a path or a mobility type of network. And there are some special considerations there. And then finally, a route-based topology. And again, we'll dig into this more, but if I'm talking about a transportation corridor, it may not make sense to do a big area-wide coverage plot if, for example, it's the exact track right-of-way for a positive train control system, or if it's an exact highway corridor that I'm interested in, then I want to think about those demands of the topology when I'm setting up my model. The next question to think about is, what do we have available in terms of geodata to represent the environment? Again, if I'm just doing an early dimensioning for a project, if somebody has asked me, hey, roughly how many sites would it take to cover this particular service area, then it's possible that I may not have terrain or clutter or anything really for that area, or maybe I've just downloaded some very low resolution terrain and I need kind of a back of the napkin estimate. SignalPro is perfectly capable and set up to do those kinds of estimates, but of course you would set up your project very differently than if you're trying to do a high detail finished design. One question to think about is, if you are doing a high detail finished design, a question to think about is how buildings are going to be represented in your geodata. Are they actual polygon building footprints with heights associated? Are they full-on building models that include wall material types and all of that? Or are the buildings incorporated into the clutter database as, you know, residential or urban categories that are very generalized? How those buildings are represented becomes very important to how we want to set up our model settings and think about building losses. And finally, how are the clutter heights being established within either the clutter database or the building database? Do we have explicit clutter heights for every location, or am I looking again at sort of generalized categories like residential or dense urban, which are just going to have an average height associated? Is this technology or this frequency band particularly sensitive to line of sight conditions, or is this a technology that's designed to operate in non-line of sight? Very often my modeling choices will vary based on whether I'm trying to guarantee line of sight or very near line of sight to all of my links. And obviously, finally, does the client or the governing agency involved require a specific propagation model? And if so, I need to understand those requirements. So before we get into path loss modeling, I touched on this a little bit. The topology of the network, whether it's mobile, fixed, or route-based, implies a particular study type. And very often, I've found that folks who maybe have gotten used to other cheap or free propagation modeling software get used to sort of doing everything with an area coverage plot, with a heat map. And if we're talking about fixed network design, such as a point-to-multipoint, then there is some lack of precision involved in an area study. And in the same way, there's an increased precision we can get out of a route study or a point-to-point link study or point-to-multipoint. So let's look at those types first, because this really does play into the accuracy of the modeling as well. When we produce an area study in SignalPro, this makes kind of the heat map results that a lot of us are really familiar with. And you can see I've zoomed way in on those results here for an example of an area study. And basically, here's what we're doing to construct the link budget. For a typical area study, we will create radial paths around the site. So in other words, for every compass direction, we'll extract out the terrain and the land use, land clutter around that site, and get the coverage at different distances going away along those radials. And so that's sort of an approximation of the coverage in every direction as we go away from the site. And then for every grid point within the area study grid, we're then saying, okay, from those closest radial points, let me make an average for each little cell that's sort of what we expect the average signal level to be across the entire space of that grid bin, or that sort of pixel area that you see here in the grid results. And sometimes these grid bins can be quite large. A typical example would be if I have a 30-meter point spacing on my output grid, then any one location is located somewhere within that 30-meter box. And if I'm standing just around the corner behind a building, then I'm going to get one signal level. And if I step out from behind that corner, maybe I'll get a completely different signal level, even though I'm still standing within that grid bin of the area study that predicted, signal level X for the entire grid bin. And so the way to approach an area study is kind of like an approximation for signal level over each of those little grid bin areas. That's the estimated average signal level within that bin. And for fixed network assets, of course, that may be lacking in the precision that we need. If we want to guarantee line of sight to an exact utility pole, then this approximation over these grid point cells is not necessarily appropriate. And so one way that people approach that is just to keep refining the resolution of their area studies. If I want a really detailed area study, maybe I'll zoom way in on the area of interest and take my point spacing down to like a 1 meter point spacing. But that's still going to be based on those radials. So if I get far enough away from the site, I can have some imprecision or some spreading of those radials that can, again, sort of smear the results or make them better as an approximation over an area, not really a specific point-to-point prediction. One point I wanted to make while we talk about these area studies is that in previous versions of SignalPro, there were two ways to do an area study. You could do the radial-line method, or you could do the direct-to-grid method, and that's set up in the study options themselves for the area study. And the radial-line method does just what I just described. We make radials at each compass direction around the site, and then the grid results are built from those radials. And the nice thing about that is that it's a nice, fast, efficient way to get results for each of those grid points. The other option was direct to grid, where we did the exact path, so the geometric path from the base station to the exact center of every grid point gets extracted and calculated instead, which means that instead of 360 radials around the site, we have to extract as many different unique paths as there are grid points within the study grid. And so the downside to the direct to grid method was that it can take a really long time to finish those calculations. And it was the only way to get rid of the problem of those radial lines spreading out as you get farther from the site. With version 9 of SignalPro, one option that you have when you set up your area studies is the new grid optimized radial method, which is a method that basically increases the number of radials calculated as you get further out from the site, so that we can solve that radial spreading problem and keep the same degree of precision out across the area study grid without actually having to calculate every last path to every grid point center. So if you're used to running area studies over a very large area, one thing you might really want to check out in the new version 9 is the grid optimized radial method, especially if you've been using direct to grid over the years for those long range sites. But again, this is really only appropriate, an area grid type study is only appropriate when we're actually trying to model subscribers that are out moving around in the environment, and they may be anywhere relative to the clutter in the environment. And for those situations, this averaged signal level across an area is a really good way to see where you do and don't have coverage. However, for any type of fixed network where the assets are not going to be moving, you can introduce a lot more precision to your studies by using either a point-to-point or a point-to-multipoint study type. And the only real difference there is whether you're looking at one specific point-to-point link or whether you have base stations and you're going to scatter a bunch of fixed subscribers out through the network area that are going to talk back to those base stations. The underlying calculation is exactly the same. And what we do for a point-to-point calculation is to extract the terrain and the clutter along the exact geometric path from the base station to the fixed subscriber, or both ends of the link path. And that means that the line of sight will be calculated with as much precision or as much detail as you have in your underlying terrain and clutter database. So in this example here, we've got a point-to-point link that's a little over 3 kilometers, and there's no worry about any radial spreading or any lack of precision in the angle of this link path, because we're actually extracting the obstructions on the exact geometric path between them. And in this case, I've decided to treat the clutter like a hard obstruction to be diffracted over. So you can see my Fresnel zone here and my direct line of sight path. This straight red line here is my direct line of sight path, and it's grazing over the top of some clutter here, and then again being blocked by the clutter here and diffracting down to a subscriber unit that's just a little bit lower than the height of the clutter here. And we'll talk about different ways that we can treat that clutter. But the important thing is that if you've got fixed assets, you really should import those fixed asset locations and use a point-to-point or a multi-point study in order to look at the connections between those devices. And this is also the essential calculation method that gets used in our mesh studies. So if I have, 1 million mesh nodes out across some service area, and I need to know how they connect to each other, with high detail clutter data, then it's actually the exact geometric paths between all those assets that the software is going to look at, rather than an area-wide study, which has, again, that sort of lack of precision. The other thing that's nice about point-to-point and point-to-multipoint studies is that the antennas can each have their own height above ground level. So if I'm interested at subscribers up on poles and down on electric boxes and on the sides of houses, I can model all of those different subscriber types in the same study with a point-to-point or a point-to-multipoint network. And that includes different antenna types and different equipment parameters on the subscribers as well. So there's just a much more detailed way to look at a fixed network. And finally, route studies. These are very often overlooked or lumped in with area-wide studies. The project we're looking at here is our positive train control demo. And very often, transportation corridors offer some unique challenges for RF planning. On the one hand, a transportation corridor through an urban area is just like any other urban planning, in that you do have mobility and you'll get different fading as you move along your route. But very often the right of way of that transportation corridor has some different environment right around it that makes propagation along that corridor, I guess, different than it would be going, out to streets and roads, just trying to cover across the entire urban core. If we're out in the open on a wide highway, then there's not going to be any nearby clutter losses. And by the same token, on a railroad right-of-way, there's open space in a lot of areas, but there can also be catenary poles and other things going right over that right-of-way that make it worthwhile to use the exact precise locations along that route, rather than doing radial lines and allowing them to spread out, and rather than doing grid points that may or may not be centered exactly on the track. What we do with the route study is we plug in the exact paths that either the railroad tracks or the highways follow, and we can run essentially a point-to-point prediction to study points that we position right in the middle of that route, so that you can get a prediction for the exact center of the right-of-way. And we also include a utility tool that can take the description of the track or the highway path and put another study line just to the left of it and just to the right of it, so that if you know your right-of-way is so wide and you want to be able to guarantee coverage down the center and also at some distance to either side of the track, then we can extract out those additional points and make your study so that it is basically 3 lines of points along here. And in that way, you can get a really precise description of coverage along the right-of-way of the track. And again, if I have really high resolution terrain and clutter data, those paths may be significantly different than what I would have calculated if I just used a standard area study and just looked at those area study grid bins and tried to look at the areas that line up with the track. For one thing, it's very hard to quantify coverage along some given transportation corridor from an area-wide study like that. It's hard to say I have 95% of the track covered, but also there's a lack of precision there. Whereas if I'm looking at the exact study points along that transportation corridor, I'm going to get a much more accurate, more precise path calculation to predict the path loss along that track right of way. The one last thing I wanted to say about this is that this study method supports flight paths for aircraft. It's not a very common application, but if you need to model ground to air or air to ground communications of some kind, you can also use the route studies for that. So the next big question that we need to think about before really selecting a path loss model and options is, again, what kind of geodata we have for this design and how that's going to impact our model selections. Up here at the top, I've got a picture of the kind of traditional USGS National Land Cover data set this is Eugene, Oregon, I think. And it's a reasonably urban area. We've got some 5- and 6-story buildings down here in the core area. And you can see this is all just classified as red, which is just urban in the National Land Cover data. And there are no street corridors shown in this. So everything that's street is classified as urban, and so is everything that's building. And so I'm not going to see propagation down street corridors with this kind of geodata. Regardless of how I set up my prop model, I won't see that sort of ducting or better propagation down street corridors as opposed to over the tops of buildings. It's all going to be treated the same, which for some systems, or again, if I'm doing like an initial dimensioning estimate, that might be perfectly fine. But then in the lower picture down here, what we're seeing is the EDX Cirrus geodata. So this is our 1 and 30 meter hybrid data that does show all of my street corridors. Those are all carved out as open. And you can see parking lots in here represented as open. And I've got actual building footprints. All my red areas are places where there definitely is a building. And in the Cirrus data, those buildings currently are represented with just an average height. So I generally know where the buildings are, but I don't necessarily know exactly how tall they are. I would want to go in and sort of sanity check the height values in my attenuation file before proceeding with the study. There is also data available through EDX or through other data vendors that has a clutter height grid associated with the clutter grid itself. So for every location in the service area, I would not only have a clutter type that says, oh, here's building and here's parking lot, but I would have a height associated with that building. Or if there's foliage, I would have an exact height associated with the foliage at those locations. And if I have that data available and at a fairly fine resolution, then I have an extremely detailed, extremely granular model of the environment. And I should be trying to leverage that when I set up my propagation model options. And when I set up the study types, I want to make sure and really leverage all of the detail of that database. A couple points I wanted to make about this is that there really are no set rules. Very often I'm asked the question, what resolution of data do I need in order to design X type of network or to design in this frequency band? And the only real answer to that kind of a question is, well, what are the needs of your planning? How much accuracy do you really need in this predictive model? Do you just need an estimate of the number of sites, or are we going to be going out and actually deploying these sites just as they're designed and expecting, you know, highly accurate predictions right out of the gates? In a mission critical fixed design, like for distribution automation in a utility network, or or some kind of critical industrial process, obviously we want to have as much accuracy and reliability in the prediction as is possible or practical. But in cases where you just need a pre-dimensioning estimate for a project that you haven't won yet, maybe there's no point in spending the money on that high resolution data. One of the nice things about the EDX Cirrus subscription is that it allows you to have really granular data available for the entire country or your entire area of interest, so that when a new project comes in, you can pull down this better, more granular data, so that even your pre-dimensioning estimates can be based on fairly detailed data. The last thing that I wanted to say about this is that the higher you go in frequency band, the more dependent in general your technologies become on line of sight. So for example, 700 megahertz is a great non-line of sight frequency band. You get great penetration through foliage screens and diffraction around corners, and so being behind an obstacle does not necessarily mean you won't have a connection. And by the time you get up to millimeter wave frequency bands, if you don't have line of sight, or if you're not extremely close to the transmitter, then chances are you just don't have a connection. And so in cases where your technology or your frequency band is very line of sight dependent, it kind of implies that you need to have much more granular data, and especially height data for your clutter, in order to make sure that if a link path is predicted as having line of sight, then it absolutely does have line of sight out in the real world. Whereas, you know, if we were designing like a public safety system down at a lower frequency band, whether you've exactly got line of sight to a real specific location probably won't matter as much, because if there are some grazing obstructions, it'll have a minor impact on the received signal level, but it won't necessarily stop the connection altogether. So it's definitely important to think about the frequency band of interest when you're thinking about what the geo data requirements are for the project. And again, if you're not sure what's available for your area, or you need to make sure that you have granular enough data for your project area, feel free to reach out to EDX and we can help you with the options there. Okay, so now getting into the actual propagation model dialog here. Let me jump over to the software and get a live version of this dialog we can look at real quick. So EDX allows you to set up multiple propagation models within the same project. So each one of these lines here in my propagation model table represents a model selection itself. So here I'm choosing between free space RMD, Anderson, Tyrem, etc. And there are various different model types here. And then we've got some categories which give us some of the categories associated with like the EDX advanced propagation module and that kind of thing. But when I set up one line in this table, I also have this additional data down at the bottom of the dialog, which is associated with that line in the table. So you'll notice here my free space plus RMD model with terrain only. I don't have any of my clutter options turned on. It's just purely a terrain-based model. But then I've also got Anderson 2D for mobile nomadic, and I've made a selection for how I want the clutter to be applied. And then I've got Anderson 2D for fixed backhaul, and I've made a different selection for how I want the clutter to be applied. And now when I go into my project, I would want to make sure that all of my mobile nomadic base stations select the appropriate mobile nomadic propagation model that I've set up. Whereas if I'm going to set up a point-to-point link, I would want to make sure that all of those point-to-point links were set up to use my fixed backhaul propagation model instead. And you can use this in a lot of ways. If you have different types of network topology that you want to account for in your project, then it's appropriate to make two different propagation model settings to apply to your mobile nomadic versus your fixed, or a model for your mesh network and then a model for your backhaul, or whatever the case may be. It can also be appropriate to have different models in the same project if you want to use a more conservative model for your downtown urban core, and then maybe relax the clutter loss values when you get out into the suburbs. And so within these different selections with the table, if I wanted to, I could also point to a different clutter attenuation file. And this clutter attenuation file, if I click edit real fast, what this gives are the clutter classes within my clutter database, and also an average height for each of those classes, so that if I don't have a clutter heights grid, then the height of all of my developed high intensity, for example, will be taken as 12 meters. And I've got two different tables here for loss from clutter at receiver and for pass-through clutter loss. And again, I might make two different copies of this attenuation file that has the same categories, but maybe different heights or maybe different loss values associated with those categories. And in that case, I'd make one model my dense urban model and one model my suburban model. And I would just assign those to sites within those different categories of, or those different parts of my service area. The pro tip that I want to share with you here is to go ahead and name this, each of your models, a nice descriptive thing that is something other than global group model 1. You know, when you first open an example project, they're all called global group model 1. But you know, as you can see, I've changed all the names here to represent what I'm doing with the model. And it's important to notice too that some of these have a supplemental data button associated with them. You know, my free space plus RMD, there's no supplemental data because that model just does what it does. But if I choose my custom model, or something like my Okamura Hata, or some of these models that have additional parameters to set, then this supplemental data button becomes active. And if I dig into this, I can adjust my different parameters within that model and choose an environment switch and that sort of thing. So let me jump back to my my PowerPoint here. As far as the model itself that you select, you know, I called out a few names just now: the free space plus RMD, the Anderson 2D, my Hata type custom model. Those model selections we'll kind of talk about a little bit in a minute, but it's important to really pay attention to these other options down here in the lower half of the dialog. These environment parameters, the K factor, ground conductivity, dielectric constant, those are going to stay the same for most modern broadband applications. If we were interested in ground waves for really low frequency technologies or something like that, we might mess with the dielectric constant or that kind of thing. But for most applications, these environment variables you don't really need to set. The exception to that is when you are up at millimeter wave frequency bands, we need to apply some atmospheric absorption and set the climate type, which those are fairly obvious, easy switches to set, but it's important not to overlook them because a line of sight path up at 50 gigahertz is going to accumulate quite a lot of air absorption over distance as well. And then again, this clutter attenuation file and which of these 3 clutter loss switches you select are completely crucial to the results that you're going to get from the path loss model. And so you'll really want to pay attention to these switches. And if you're not sure which of the best of these is, or which of these is best at representing your particular conditions in the environment, then we have options down here in the bottom corner to test your predictive model against measurements that you've gathered in the field, assuming that those measurements exist. And model tuning is a little bit outside the scope of today's discussion, but I wanted to throw it out there that we do have facilities built right into this dialogue to test and see how accurate your model is compared to drive test data or walk test data. Or if you've got a fixed network, you can poll each of your fixed subscribers and get averaged measurements for their signal levels and test the model settings that you have to see how well they correlate up with reality. So now let's talk about the types of propagation model, or the propagation model names. There are 2 really main types, 2 main approaches for making a path loss estimate between any 2 antennas. We think of those as physical or deterministic path-based models. And in that category, the model is trying to really extract the exact terrain elevations and the exact clutter elevations along the geometric path from transmitter to receiver. And anywhere that it finds an obstruction of the line of sight signal, we account some loss for those obstructions. And there may be some correction factors and things applied to that. But in general, a physical model is trying to, in effect, simulate the direct path between any 2 antennas and really make a detailed picture of that path to account for losses. Empirical, or what I sometimes call distance-based models, are designed to work well in situations where you do not have a highly detailed model of the environment. So if I only have very low resolution terrain data, and maybe I don't have any clutter data at all, or maybe the clutter data I have is badly out of date or too coarse or something like that, in those cases, the nice thing about an empirical model is that it's very consistent with the results it gives you, and it can be adjusted easily. Most of them have some adjustment factor to say, oh, I'm in suburban now, so reduce the amount of loss I get, or I'm in urban, so increase the amount of loss I get. But it's important to understand that these models, while they may be recommended for certain applications, they're only going to be sort of a rough estimate of propagation distances. So for example, if I use the Okamura-Hata type model, I may not see critical shadowing due to terrain. If my base station is right next to a big hill that's much taller than the base station, the Okamura-Hata model is not going to extract the terrain along that path, and it will not see that hill. So when I use these empirical models, the coverage footprint that I see, if I were to run an area study, I would get these almost circular coverage footprints where there's not going to be much distance or difference in the propagation distance. Those can be required by the client, though. For example, the FCC models, if I'm running an FCC interference contour study, that agency has a requirement for which model and which set of distance-based path loss curves I have to base that interference contour on. So in some cases, these empirical models may be required by your client or required by the governmental agency involved. The rest of the time, since you've got a high detail planning tool called SignalPro, and since you probably have access to high resolution Geo Data for terrain and clutter, it makes a lot more sense to use a physical path-based model, such as the Anderson 2D, the Free Space plus RMD, or the TIREM. And these are all physical path-based models with a few minor variations between them. Longley Rice is an old but fairly popular terrain-based model as well. And then there are some specialty ones here. The EDX simplified indoor model is a wall crossing model specifically for indoor environments, and but it's still a physical, path-based model. And then our Anderson outdoor to indoor model is unique in that it is our outdoor Anderson 2D model for any outdoor portion of the path. And then it's the simplified indoor model, the wall crossing model, for any portion of the path that's indoors. And so SignalPro is unique in that we have a propagation model that will cover the totality of the indoor and outdoor path and give you one path loss prediction for it, so that you can do indoor-outdoor coordination studies, campus-wide studies, that kind of thing. And then finally, we offer 2D and 3D ray tracing with the advanced propagation model. And that uses building polygon data where your buildings need to be defined not only in terms of sort of where the polygons are, but you assign wall material types to the building exterior, or if you're doing indoor-outdoor studies, you assign material types to all the walls and things inside the building. And the nice thing about ray tracing is that it can diffract around corners and reflect off of the faces of buildings and things like that. So you can get a very good sense of multipath and how that will impact your propagation. The downside to ray tracing is that it takes a long time, and you need to have really high resolution, high detail building data in order for the ray tracing to really provide any reasonable results. In the reference manual appendices, which if you just go to help and reference manual appendices, you can get to the very first chapter in that appendices is the chapter on propagation models, where we break down all of the model names that are available in SignalPro. We break down what frequency band they're appropriate for. And some of these models are absolutely not designed to go outside the frequency bands listed here. And then we also have this table of which models can have which processes applied to them. So add clutter loss, add clutter height, etc. And so if you have any questions about the particular models, I recommend taking a look at those reference manual appendices and familiarizing yourself with what the model does. We've got these additional switches here that can be applied to any of these models for ground reflection, Fresnel zone loss, and troposcatter and building data. The important thing to recognize for the troposcatter is that this is a troposcatter over the horizon component, but it is only designed to be used for over the horizon interference between terrestrial networks. The ITUR has a recommendation for accounting for interference from other over the horizon sites, and that's what this troposcatter module is for. So if you're not doing that specific use case, most of the time this switch will be off. And ground reflections, similarly, you'll want to switch that off for most applications, unless you're at a very low frequency band or over really smooth terrain somehow. Fresnel zone loss, on the other hand, should pretty much always be switched on, unless you have some really good reason for not wanting to include it. And finally, the clutter settings here. And I know we're getting short on time, but this is the place where I always want to get out my soapbox and stand up on it and make sure everyone understands what each of these three methods does and can select the appropriate one for their network topology and their specific needs. Again, the clutter attenuation file here gives the heights and the loss values associated with the different clutter types. And then we have one of these three switches can be switched on to apply clutter loss to the model. And the add clutter loss switch, a lot of times people will just reflexively turn that on. But the thing to understand about that add clutter loss is that it only looks at the clutter at the receive unit location, compared to the pass-through loss and the add clutter height to terrain height methods, which look at clutter along the entire length of the path. And so what do I mean by that? This link path here is being calculated with just the add clutter loss option. And so none of the foliage clutter along this hill is going to be considered. We've got line of sight above the terrain, and this hard edge line here you see is actually the terrain elevation. And there's no clutter along this path. You know, that these red and orange categories represent buildings, but you'll see they're also not, their height is not being accounted for. And all we're doing is accounting for the clutter right at this mobile subscriber location and saying, okay, if the subscriber is in medium density urban, then we take off this many additional dB of signal level. So you can think of this as like clutter specific margin at the subscriber. And the rationale behind this is the traditional way to do land mobile planning, where you have that lower resolution USGS type clutter data. So in other words, this clutter data up here, where everything in the urban core is just called urban, it's appropriate to just look at where the subscriber is and say, okay, you're in urban, so I want to apply an extra 12 dB of loss to the entire path, because I don't really know how the building clutter is going to intersect with this exact path. We just know that the subscriber is in urban and we want to account for it. So again, the add clutter loss is like subscriber location based margin. If I'm doing any kind of fixed design, this approach is probably inappropriate, because in a fixed network, my subscribers are usually going to be located in some situation where they're not buried down in the clutter. They'll be up on a utility pole or something of that type. And in those cases, it's clutter along the entire propagation path that we're interested in. So we've got two options. The clutter pass-through loss is going to evaluate clutter along the entire length of the path, and anywhere that the line of sight path is going through a particular clutter type. So here you see this hard edge green line is my terrain elevation, and I've got some urban clutter sitting above that. So these are buildings, or at least the possibility that there are buildings there are represented in my clutter database. And so anywhere that it's going through that clutter type, I apply the path loss based on the distance that line of sight path is going through a particular clutter type. And you can adjust those loss values according to your measurement data, so that, you know, your building classes give you a whole lot of loss, and maybe your light foliage classes will give you much less loss. And this is very appropriate to non-line of sight technologies, where you may have clutter anywhere along the path and you really want to account for it because you've got high resolution clutter data. And then finally, the add clutter height to terrain height is sort of the most conservative way that you can apply clutter to the path. Here, we're going to look at the height of the clutter along the entire length of the path, and rather than assume that the path will be able to penetrate through that clutter, we're going to diffract over the top of it. And when I set this up, I have this clutter exclusion distance value here that this is like a setback distance where I'm saying, okay, if I put, let's say I put 25 or 0.025 kilometers in there, I'm saying I expect to have at least 25 meters of free space around my antenna before there's any clutter obstruction. So that's a way of saying, well, I've got at least some free space around my antenna. And then when it calculates the loss due to clutter, it's going to diffract over the top and apply losses based on those diffraction angles, as though the clutter was a hard obstruction to be diffracted over. And this is really appropriate for any line of sight system. If we are up looking at the millimeter wave frequency bands, or even up at 5.8 gigahertz, or maybe a little higher, the technology really needs line of sight or very near line of sight before you start accumulating loss that is just going to be too much. And so the add clutter height to terrain height method can be really perfect when you want a very conservative prediction for those fixed networks. So those three clutter methods are really crucial to think about. Let me review those one more time. I want to either use add clutter loss for subscriber location specific loss, or I want to look at pass through clutter and do penetration through the clutter over distance, or I want to diffract over the clutter and treat the clutter as just a worst case. And if I have very high resolution clutter data and clutter height data, this may be the most appropriate approach for any frequency band, really, if the data is detailed enough. And which one of those settings you make will have a really strong impact on the accuracy of the propagation model results, regardless of which of these actual propagation models you choose. So to sum up, you'll want to choose the type of propagation model, but that's not where the decision, you're not done with the decision at that point. You also want to choose one of these clutter loss methods and really sanity check the values that you find in that attenuation file associated with those clutter types. And if you're still not sure which propagation model you can use, you'll find that handy suggest model button here at the bottom of the dialog, where I can say whether I want a site-specific physical model or a quick and simple empirical model. And then I select a few other things about what I'm doing, whether I'm doing fixed broadband, what my frequency band is, and so forth. And it can suggest for you some empirical models to get a rough distance estimation, or it can also suggest the appropriate physical model for that frequency band and so on. And this is really just a rough suggestion. If you need more input or you want to talk through your model selections, finally pick up your rotary dial phone and call us up at EDX. We'd be happy to have that conversation with you. I know we're right at the top of the hour here. Rory, I wanted to kick it back over to you and see if there were any questions that came in at the end there.
Absolutely. So I did have a few come in here. One of them is at some point you were talking about the Anderson 2D model, and you mentioned 3 dB margin on that model. How is that actually used in affecting the prediction when using the Anderson 2D model?
Sure. This margin field works the same way regardless of which propagation model you choose. Basically, the margin that you enter here, it's design factor. I'm just saying for every path, go ahead and apply 3 dB of additional path loss just to make my prediction that much more conservative. And the reason I did that for my mobile nomadic model and not my fixed backhaul model is again, I want to treat it like design factor. I know that my subscriber is close to the ground and may have some additional losses associated with that. And so I just want to add another 3 dB onto my model to make it a little bit more conservative. The percent of location and percent of time fields kind of do the same thing. If I increase these values beyond 50%, they start adding more path loss to try and account for variability within the environment. Most of the time, I recommend leaving these set at 50%. And if you want to add design factor onto the model, use the margin field here instead. Model reliability and variability is a whole other topic that we could get into. So feel free to email us or give us a call if you want to dig into those details a bit more. Any other questions?
The other question I had was on reliability. And so let's say someone has to come up with 90% reliable prediction. How would they account for that in setting up their project?
Sure. This is something that's actually changed in the industry over the last 10 years or so, where it used to be sort of the traditional way to do land mobile planning was to select a model like the Longley Rice, which is a physical terrain-based path model, but it's not terribly precise in how it treats terrain obstructions. And I would just do a coverage map. In the old days, I would just do like a received signal map, and I wanted to apply additional loss to my prediction so that if I predict a given signal level for one grid location, then, say 90% of the time out in the field, I'm going to measure a higher received power value than what I predicted. And so I would increase these to 90%. And the amount of additional loss was based on tables provided by the NTIA for how much additional loss or how much fading we expect to see over time and how much Raleigh fading. But the important thing about this is if you do this here, this affects the path loss for every other prediction downstream, including your interference predictions. And we don't want to add additional path loss to our interference prediction. So in more modern approaches, both with our software and with other planning tools, it's more standard to try and predict the path loss as a mean average signal level. So I'd leave these at 50% and not try to account for my variability here, but instead I would go and set up studies which account for that fading. So instead of just a receive power at remote study, I could go in and select my percent service availability. And that study type is meant to take the average signal level that the path loss model generates and then apply some fading according to these reliability methods that we've set up and tell you what percentage of time your link has sufficient fade margin, even with Raleigh fading and even with rain fading. And so the general recommendation nowadays is to try and have your path loss model hit the average measured power. If I went out and did drive test data, I want to see fairly exact agreement between my prediction and my measurement. And then if I want to build design factor onto that, I would apply additional loss for the subscriber. Or if I wanted to look at availability and fading, I would use the specialized studies that we've designed specifically for that, instead of just punching in 90% of time and location here. Now, the reason we still have those fields is that sometimes either the customer or the government agency requires that your path loss prediction be done with the particular values in those fields because they're referring to a government recommendation. So those fields are still there, but the methods for planning have kind of moved on in recent years from that. Are there any final questions, Rory? I know we've gone a little bit over time already.
Yeah, it looks like that's everything that came in that relates to the webinar. There were a few questions that came in that I mentioned we would answer after the fact to them that it didn't relate to the webinar stuff specifically. So at this point, yeah, we've answered all of the questions that have come in, and we're ready to let everyone get back to work.
All right. Well, hey, I want to thank everybody for joining us here today. Uh, again, this was a pretty quick overview. I hope it gave you some food for thought. And if you've got any questions about how to get better agreement between your SignalPro predictions and what you're finding in the field, please don't hesitate to call us up and start a conversation.
Absolutely. Thanks again, everyone, for joining. If there's any questions on things that have come up in this webinar, you can always reach out to our support line, support@edx.com, and that will allow you to ask questions and follow up with anything that might come up. So thanks again for joining, and everyone have a great day.